All right, guys, so this is going to be our final video for 4.3 as we kind of wrap up everything that we've been talking about in terms of how can we really compare the first, second derivatives to the original function itself. So let's look into some goals for this video. So we want to really focus on using the properties of the first and second derivative, concavity, and inflection points and put it into some real life application. Where does this stuff actually happen in real life? We've already kind of talked about how derivatives really focus on real life circumstances, and we deal with acceleration and velocity, and that's exactly where we're going to take it in this example specifically. So it says a particle is moving along the x-axis with the position function shown below. Find the velocity and acceleration and specifically describe the motion of the particle. And so we first got to think about what our goals are of this question. So let's kind of look at some success criteria here. So first and foremost, we need to find velocity. We know we need to find acceleration. And then the second portion of it, or the last portion of it, says describe the motion. So think about what it means to describe the motion of the particle specifically. The first derivative is going to tell us which direction it is going to be going, right? Because velocity is going to tell us if we're increasing, that means that we are going to the right, so we're going forward. And then if it's going decreasing, or if it's starting to get negative on us, then we're going to start moving backwards and we're going to go to the left of things. And so that's kind of what velocity is going to tell us. So velocity will tell us right or left. And then acceleration, well, think about what's acceleration going to be. We want to know what the second derivative tells us. The second derivative test tells us about the concavity of it. And so think about what it means for things to be concave up or concave down. When you're going concave down, you are starting to start like a strong slope as it goes up, but then you're starting to get your slope smaller and smaller and smaller and smaller, and then even negative once it gets past zero. So when you have concave down, think about it for a second. What does that mean in terms of the acceleration? Hopefully you guys can kind of come up with that when you are concave down, that really means a particle or something moving is actually decelerating. And then when we are concave up, that means we are accelerating. So we are really trying to find out whether we are decelerating or accelerating based on the concavity itself. So increasing velocity means we're moving right, all right? Decreasing means that we're going to be moving left. Concave up means we're accelerating. And then concave down means that we are decelerating. So let's kind of put this into motion first and foremost. Well, we know we need to find v of t. Well, v of t is going to be x prime of t. So v of t is equal to x prime of t. So in this case, we get 6t squared minus 28t plus 22. And I'm going to factor this out because we know we need to know those critical points as to where the graph or the derivative is going to be zero, so we can determine when it's increasing or decreasing using that first derivative test. So I'm going to go ahead and factor this on out. I see that there's a 2 in common with everything, so I'm going to factor that 2 out. And what we're left with, we get t minus 1 multiplied by 3t minus 11 there, okay? And so we just factored it out just to get the factors of this function so we can go ahead and find out where it's going to equal 0. And then let's just go ahead and find acceleration here so we have both of them to look into. So acceleration is going to be v prime of t or x double prime of t. So in this case, the derivative of the velocity is going to be 12t minus 28. Once again, I want to factor this out because we need to know when the acceleration is going to hit 0 for t. All right, and so in this case, we're going to set this equal to 0, and we're going to see that we have a 4 involved with both of them. So let's factor out the 4, and we get 3t minus 7 here. So here's our two functions of velocity and acceleration. And now let's set each of them equal to 0 so we can find out what's going to happen to t when the function but kind of bottoms out at 0, so we can find some critical points specifically here. So we can see that for velocity, let's go back to red here. For velocity, we can set this equal to 0, and so we know that, well, 2 is not going to really matter, but t minus 1 set equal to 0 will get us when t equals 1, and then when 3t minus 11 equals 0, we get t equaling 11 thirds. And so that's going to be kind of our focus point here. So let's draw our number line. We have a critical point at 1 and a critical point at 11 thirds, and we actually have a third critical point. It's going to be here at 0. Why is it going to be 0? Because that's our starting point. We know that as a specific end point that it's going to be, because it's not going to be anything less than 0, so we're going to put 0 involved in there as well too. And so we basically just need to see what's happening between 0 and 1. Now, to save a little bit of time, we're going to kind of just, I'm going to kind of give you a little bit what's happening here. So choose anything between 0 and 1 and see what's happening. So let's just choose, I don't know, 1/2, right? So you want to know what the difference between 0, 1/2, and 1 really is going to be. So when, I guess it's x, not f. But when we're dealing with x of 0 in this case, well, that's going to be 0 minus 0 plus 0, and then minus 5. So that's going to be here at -5. And then you want to know what's happening when x of 1/2 is going into play here. And again, just because things are going to take a little bit of time, we can kind of see what's happening from 0 to 1 instead. So x of 1 in this case, well, it becomes 2 minus 14. So 2 minus 14. 2 minus 14 plus 22 minus 5 in this case. I guess you didn't really need to find out what was happening at 1/2 anyway, because you can see what's going on between 0 and 1 once you do the math. So 2 minus 14 plus 22 minus 5 should give us 5. So from 0 to 1, we know that is increasing. So that's going to be a positive. And now we need to see what's happening specifically at 11 thirds, all right? So let's find out what's happening at 11 thirds. So x of 11 thirds in this case, and this is going to be a little bit of a tricky one, so our calculators will be extremely helpful when we do this one here. So we're at 2 times 11 thirds, and that's going to be quantity cubed, minus 14 times 11 thirds quantity squared. And then we have plus 22 times 11 over 3 minus 5 in this particular example. All right, so let's kind of just take a look here, and just to simplify this out a little bit, we have 2 being multiplied by 11 over 3 cubed. Well, 11 cubed in this case will be 1331 over 27. And then we have 11 squared, which is going to be 121 over 9. And then plus 22 over 22 times 11 thirds. So 22 times 11 gives us 242. And that is not divisible by 3, so that doesn't help us out too much. 242 over 3. Does 131 divided by 27? That is not even either. So 2 times 1331 is 662 over 27. And then 121, unfortunately, also is not divisible by 9. So 14 times 121 gives me 1694 over 9 plus 242 over 3 minus 5. Now this is kind of getting a little bit obnoxious here with our values that we are dealing with. So obviously when you're substituting in the calculator, it makes it a little bit easier for us. But we can see what's about to happen here is that this is about to give us a negative value. And so it's going to end up decreasing from 5 to 11 thirds, all right? So we can kind of see this is going to be some negative values when we get in here. So we're now decreasing from 1 to 11 thirds. And then you just choose something to the right of 11 thirds and see if that's going to be anything bigger. And in fact, it does. All right, and we could have chosen, I mean, anything really. I don't know, 5 if you really wanted to, something that makes the numbers simpler for us to go ahead and solve there. And we see that in this case, it's going to be increasing here. And so let's take into perspective what this actually means. From the interval from 0 to 1, it is increasing. The behavior of x is increasing. So that means that our particle is really moving to the right, or it's going in a positive direction. Then as we're decreasing from 1 to 11/3, that means our particle is actually moving left. So it's kind of going backwards from where it started from. And then after 11/3, for the value of t, we start to increase again. And so we start to increase again. And so then we're starting to move to the right from 11/3 on. So if we're talking specifically intervals from 0 to 1, I guess it's not included here. From 0 to 1 and from 11/3 on to infinity, we are moving right. And then from 1 on to 11/3, we moved backwards and we're moving left. So let's wrap up this problem by talking about what's happening in terms of the second derivative. And remember, our goal was to say, hey, when are we accelerating and when are we decelerating by using our second derivative? So our only critical point that we're dealing with for our second derivative is when t is equal to 7/3. So let's take a look here. Let's rewrite our second derivative. Our acceleration was 4 times 3t minus 7. So t is going to equal 7/3 when this equals 0 here. And so our only critical points are at 0, because that's where it starts, and then at 7/3. So on our number line, we have 0 and 7/3. So you want to know what's happening between 0 and 7/3, so we're curious between here, and then after 7/3 as well. Well, once again, just to kind of save some time, you can choose any value in between 0 and 7/3. Choose, I would say, probably 1, or I guess in this case, they give you the acceleration at 0. You don't really need to find anything in between as well. So let's just kind of find out. We already talked about at 0. When it was 0, it was -5. And then what's the value at 7/3? Once again, if you have the graphing calculator, it makes things a lot easier for us. But we can see that it gets a little bit smaller than -5 at 7/3. So we're actually going to be decreasing from -5 or from 0 to 7/3. And then finally, choose something to the right of 7/3. Anything to the right of 7/3, see what's happening from 7/3 on to infinity. And we can actually see that it's going to be increasing in this case. And so think about what's happening here. When this is decreasing, we have concave down. And then when it's increasing, we have concave up. And so we said that when we're concave down, this really means that we are decelerating from 0 to 7/3. And then we are actually accelerating from 7/3 onto infinity. So there's kind of a little bit of an insight as to what we're really looking at in terms of why do we use our first and second derivative test, and how does it kind of help us determine some things in some real life applications. So let's just kind of recap real quick on the example. We wanted to talk about what specifically is happening throughout the functions or the particles, time in motion. We found out when it was going right and left by its velocity, and then we found out whether it was decelerating or accelerating by its acceleration or its second derivative test. All right, guys? So that's going to wrap it up for 4.3, putting it into some application, and on to the next one.